For our last lesson about series, let's talk about a special type of series which includes a variable x. So let's say we have these examples. The summation of x raised to n, that is 1 plus x squared plus x cubed and so on. Or we have this series of x minus 1 raised to n all over n factorial. In general, if we have a series of this form, series of x minus a raised to n with coefficient c sub n, then we call this a power series. So given a real number a power series about the real number a, or power series centered at a, is an expression of the form series of x minus a raised to n times the coefficient c sub n, where x is a variable and c sub n is a constant for all natural number n. So if n is equal to 0, we have x minus a raised to 0, that is just equal to 1. So we only have here the coefficient c sub 0. If n is equal to 1, we have x minus a alone times the coefficient c sub 1 plus x minus a raised to 2 times coefficient c sub 2, and so on for any natural number n. Power series may look like our usual polynomials, but that isn't always the case. If after some terms in our series, the constants c sub n are always 0, then yes, our series here is a polynomial. Otherwise, we would have infinitely many terms, hence it is not a polynomial. First, let's go back to our examples of power series. We have this series of x raised to n, 1 plus x squared plus x cubed, and so on. So we can write this as x minus 0 raised to n to emphasize that the center of this power series is a is equal to 0, and the coefficient for each term is equal to 1. It just so happened that all the terms in the series have the same coefficient that is equal to 1. So we write that this series, sum of x raised to n, is a power series centered at 0 with coefficients c sub n is equal to 1 for all natural number n. How about our second example, x minus 1 raised to n all over n factorial, where n runs from 0 to positive infinity. Here we can already see clearly that it is a power series centered at 1. Comparing it to the general form of power series, a is equal to 1, and that the coefficients c sub n is equal to 1 over n factorial. How about this series of 3 minus 5x raised to n all over 2 raised to n, where n runs from 0 to positive infinity? First, let us expand this series. If n is equal to 0, our numerator will just be equal to 1. And in our denominator, we have 2 raised to 0. Well, that is also equal to 1. Plus, when n is equal to 1, we have 3 minus 5x all over 2 raised to 1. Plus 3 minus 5x squared all over 2 squared, and so on. This may not look like a power series right off the bat, but we can transform first our series. What we can do here is factor out negative 5 in our numerator. So negative 5x divided by negative 5, that will just be x. And positive 3 divided by negative 5 would be negative 3 over 5. To factor out negative 5, take note that it is under the power n, so we have negative 5 raised to n. And now let's just complete the series all over 2 raised to n. And now we can see that this form of our series is similar to the general form of a power series. The center is 3 over 5, and the coefficients are of the form negative 5 halves raised to n. Now let's give some examples of series that are not power series. For our first example, we have series of 1 over x raised to n, or the series of x raised to negative n. This is not a power series because we have negative exponents. For the second one, we have x minus a raised to 1 over n for any real number a. We have rational exponents, so that is not also power series. While for the third one is very obvious because we have trigonometric functions in our series. Now that we know what power series are, our next question is, what is our goal? Our goal here is to find values of x such that the power series is convergent, or simply find x so power series converges. Say for example, we have this series, the sum of x minus 1 raised to n all over n factorial. If we replace x by 0, what will happen to our numerator? It will be 0 minus 1, or simply negative 1, raised to n. And our question is this series convergent? Or how about if x is equal to 2, we have 2 minus 1 raised to n, or simply 1. So the series is now 1 over n factorial. Is this resulting series convergent? The set of all such x that makes our power series convergent is what we call the interval of convergence of the power series. Interval of convergence, or what we call IOC, of a power series is the set of all values x, which is a real number, for which the resulting series converges. And the radius of convergence of a power series, or in short ROC, is half of the length of its interval of convergence. Given a power series centered at A, the interval of convergence can be only one of the following: a set containing only one element, and that element is the center of the series, or the whole real number line, negative infinity to positive infinity, or an open interval from a minus r to a plus r. That is, the center of that interval is a and the radius is r. Observe that in all cases, the center a is always inside the interval. So in the interval of convergence of a power series is never empty. Also, for the third kind of interval of convergence, the open interval a minus r to a plus r, the interval actually can be closed or can also be half open and half closed as well. But for our class this semester, we'll only consider open intervals for our IOC. So there is no need to check convergence at the endpoints of each interval. If the IOC is a single element A, then its corresponding ROC is 0. If the IOC is negative infinity to positive infinity, then ROC is infinity. But if we have the open interval a minus r to a plus r as our IOC, then the ROC is r. In most cases, the ROC and IOC can be obtained using the conditions of the ratio test. Let's try that in our example 1. Find the ROC and IOC of the sum of x minus 1 raised to n all over 2 raised to n times n squared. So for us to use the ratio test, let us let a sub n to be equal to x minus 1 raised to n all over 2 raised to n times n squared. We cannot use ratio test if our a sub n's, or at least one of our a sub n's, is equal to 0. So here we cannot let x to be equal to 1. But if x is equal to 1, we are already sure that the resulting series, which is equal to 0, is already convergent. So keep that in mind, that if x is equal to 1, the series is already convergent. It is already convergent at the center of the power series. But just for us to use the ratio test, we must write here that x is not equal to 1. So let's proceed. Let us get the limit of the absolute value of a sub n plus 1 all over a sub n. So let us write here the absolute value of a sub n plus 1. There is no need to write absolute value in our denominator since that is always positive, all over a sub n, or times the reciprocal of a sub n. So times 2 raised to n times n squared all over the absolute value of x minus 1 raised to n. We have x minus 1 raised to n plus 1 all over x minus 1 raised to n. If we cancel n terms, we are left with x minus 1. For 2 raised to n all over 2 raised to n plus 1, we can also cancel n factors. So we have here 2. And so under the limit, we are left with n squared all over the square of n plus 1, or n squared plus 2n plus 1. the limit is of the form infinity over infinity. So what we can do is multiply this by 1 over n squared all over 1 over n squared. So we have the limit of 1 all over 1 plus 2 over n plus 1 over n squared. And the limit of that as n goes to infinity is equal to 1. And thus, the limit of a sub n plus 1 all over a sub n is equal to x minus 1 all over 2. So in our ratio test, the series is convergent if the absolute value of this limit is less than 1. So by the ratio test, the power series converges if x minus 1 is less than 2. That is, if x is between negative 1 and 3, right? Because the absolute value of x minus 1 less than 2 means x minus 1 is between negative 2 and 2. And we can just transpose negative 1 on each side of the inequality, and so we get negative 1 and 3. On the other hand, if the limit of a sub n plus 1 all over a sub n is greater than 1, that is in our case, if the absolute value of x minus 1 is greater than 2, then the power series is divergent. So in our number line, by ratio test, it is convergent if x is from negative 1 to 3. Here we can clearly see that the center of this interval of convergence is 1, and that is why the center of our series is also 1. Moreover, the radius of this interval is equal to 2. We don't have to draw a number line just to solve for the radius of convergence. What we can do is get the length of the interval. So here we have the absolute value of the endpoints, negative 1 minus the endpoint 3, then get the half of that length. Therefore, here we have r is equal to 2, and the IOC is equal to negative 1 to 3, where r here is ROC, the radius of convergence. Let's solve number 2. Find the ROC and IOC of the sum x raised to n all over n factorial. Let us let a sub n be equal to x raised to n all over n factorial. Again, to use the ratio test, a sub n can never be equal to 0. So x must not be equal to 0. But again, if x is equal to 0, we are already sure that the resulting series is convergent. So let's proceed with getting the limit of the absolute value of a sub n plus 1 all over a sub n. So let's get first a sub n plus 1. We have the absolute value of x raised to n plus 1 all over n plus 1 factorial. There is no need to put the absolute value around n plus 1 factorial since that is always positive. Times the reciprocal of the absolute value of a sub n, that is times n factorial, all over the absolute value of x raised to n. Here we have x raised to n plus 1 all over x raised to n, that is absolute value of x. And for n factorial all over n plus 1 factorial, we are left with n plus 1. Take note that the absolute value of x here is independent from the variable that we are getting the limit. That is, the variable is n. So the absolute value of x here can be written outside the limit. And the limit of 1 over n plus 1 as n goes to positive infinity is 0. Therefore, the limit of the absolute value of a sub n plus 1 all over a sub n is always less than 1. So for any value of x, our series is convergent. So in our number line, for any values of x, if we try using the ratio test, we always get less than 1. Therefore, the IOC is the whole real number line negative infinity to positive infinity, and the radius of convergence is infinity. Lastly, for example number 3, find the ROC and IOC of the sum of n factorial times x raised to n. Same routine, let us let a sub n to be equal to n factorial times x raised to n. Again, to use the ratio test, a sub n can never be 0. So here we must not let x to be equal to 0. If x is non-zero, we have the limit of the absolute value of a sub n plus 1 all over a sub n is equal to the limit of get first the a sub n plus 1. So that is the factorial of n plus 1 times x raised to n plus 1 all over a sub n. And if we simplify this, n plus 1 factorial all over n factorial will give us n plus 1. And x raised to n plus 1 all over x raised to n will give us x. X is independent from n, and we are getting the limit as n goes to positive infinity, so we can just put x outside the limit, then get the limit of n plus 1. And the limit of n plus 1 as n goes to positive infinity is positive infinity. Clearly, positive infinity is greater than 1, and by the ratio test, the series diverges for all x not equal to 0. So in our number line, the only value for which our series is convergent is when x is equal to 0, or that is when x is equal to the center of the series. Hence, our IOC is equal to the set of one element 0, and the ROC, or the radius of convergence, is equal to 0.